right? Okay. All right, so I don't think the recording missed anything because, we just talked about that at the end of last class. So for anyone watching the recording, you can just go back and look at that. Okay, so we're going to prove this. Now, the first thing that we want to do is prove that basically we can, by restricting the function to a small enough neighborhood, we can make it bijective. Okay, that's the first thing that we want to do. And to do that, we're going to use the fact that f prime of p is not equal to 0. So suppose that f prime of p is not equal to 0. And I'm going to say, without loss of generality, assume that it's actually positive. Okay, so without loss of generality, suppose f prime of p is actually greater than 0, okay? Because if it's less than 0, well, you'll see that the argument is going to be almost identical. Like, we're not actually going to use this for a lot. So f prime of p is positive, but f prime is also continuous. Is continuous at p. And so what did we learn, right? Don't worry about the fact that it's f prime. We learned previously, I think it was one of the bonus questions in one of the assignments. We've learned that if you have a continuous function which is positive at a single point, then it is in fact continuous on an entire interval, right? So since f prime is continuous at p, there is an interval, and we are very suggestively going to call that interval u, containing p, such that f prime of x is greater than 0 for all x in u. Okay, do you remember that? I don't remember what assignment it was from exactly. It probably would have been in and around continuity, but it's one of these things that we had to do. And if you haven't proven that one yet, I strongly suggest that you do. It is a super important theorem, or not a theorem, maybe it's a lemma. We're going to use it a couple more times in this class as well. And then, if you go and take 257 or 237, even if you go to St. George, you're going to use it a ton there. Okay, so it's really important to know. And the proof is relatively straightforward. It's one of these really nice ones where if you draw a picture, the proof falls out of it very, very quickly. Okay, so make sure that you go and prove it. So here, of course, is kind of weird because in those cases, we proved it for the function f. Here, we're applying it to f prime, but that's okay because we know f prime is continuous. Okay, so I know now that f prime of x is greater than 0 for all x in u. And before I stated the inverse function theorem last time, I stated a lemma that says if you know that your function is has a strictly positive derivative on an entire interval, then it's actually strictly increasing there, right? So from the lemma, and so again, I'm kind of saying the lemma, but if you go and you check what we did last time, you'll see we did a lemma right before the inverse function theorem. So from the lemma, f prime is thus increasing on u, and hence injective. Right? Because increasing functions have to be injective. I think we proved this earlier in the year. And if I didn't prove it, I'm pretty sure had to do it for an assignment or something, right? So thus f prime is increasing on u, and hence is injective. Since it's injective, now what we're going to do, this is going to seem like a bit of a cheat. We're going to take v to be f of u, right? And now our function is injective because we know it's injective on u, and it's also going to be surjective onto v. Right, so that if we define this thing that I've been calling f hat, which is again just the restriction of f to u, right? So it still maps x to f of x. It's just that it has a different domain and codomain. F hat is now bijective. Right? Because our function is both injective and surjective on u Injectivity followed because we knew that we were strictly increasing. Surjectivity is because we just defined V to be the image of U, right? So that guarantees that it's surjective. Okay, so great. So that actually takes care of this first part where it says if f prime is not 0, there exist neighborhoods U containing P and V containing f of P such that this thing is bijective. Okay, so because it's bijective, we know that f hat inverse exists. So what we need to show is that it is C1, right? It is differentiable and its derivative is in fact continuous. Okay, so we know that f hat inverse exists since f hat is bijective. Okay, great. And moreover, we know that it's continuous. Why do we know it's continuous? Okay, somebody tell me, why do we know f bijective implies monotone and monotone implies, so Nicole, you're absolutely right, but let's finish it off. So monotone enough without saying a little bit more doesn't imply that the inverse is continuous, but what did we very recently prove? Exactly. From the exam, you proved that if you have a strictly increasing or a strictly monotone function, then its inverse is continuous, right? So we're now going to use that exam, that test question that you all did on last Friday. And even if you maybe were a bit confused about that problem, it's correct because I put it on a test, right? I wouldn't put something wrong on a test. So moreover, f hat inverse is continuous on V. And maybe let me put in brackets here by term test 2. What was that? That was the third question, I think, right? So by term test 2, question 3, we know that f hat inverse is continuous. So now all we need to show is differentiable or C1-ness, right? We have the continuity condition. Okay, so what we're going to do is we really have to leverage, again, the fact that we know that f is differentiable at P, right? So since, well, here, we're going to do, this is actually going to be an epsilon delta proof. So we're going to say let epsilon greater than 0 be given. And again, because I'm not doing rough work, you might be a little confused about where I'm going here, but we'll stop at the end and we'll kind of zoom out and take a look at, what exactly it was that we proved and try to make, try and see whether or not it made sense. So let epsilon greater than 0 be given. Okay, so since f is differentiable at P, we know, all right, here, I'm going to write down something a little bit weird, and then we're going to make sure that everyone's okay with it. I'm going to do the x approaches P definition. F of x minus f of P is equal to 1 over f prime of P. Okay, so that's weird, right? But let's make sure that everyone is okay with what I've written down here. What you'll notice is that thing on the left-hand side is 1 over the, if I were to write down the definition of the derivative, normally it would be f of x minus f of P in the numerator divided by x minus P. And so it looks like I've taken the reciprocal of everything, right? And that's exactly what I've done. That's why I have 1 over f prime of P on the right-hand side. And I'm precisely allowed to do this because I know that this limit exists and is not equal to 0, right? Our limit laws say, if you know that the limit exists and the limit of the denominator is not equal to 0, then you can take the reciprocal of everything, and the limit of the reciprocal is the reciprocal of the limit, right? So I know this exists, and I am allowed to do this. Does anyone have any issues here? And you can see again how important it is that f prime of P is not 0, right? We assume that to begin with. So all I've done here is take the limit of the definition of the derivative and done 1 over everything. Okay, and I'm allowed to do that because the derivative is not equal to 0 here. Okay. If anyone is objecting to that, I could probably do a couple more steps. So if you want to, just say something. But if not, I will assume it's okay. I don't see any objections. Thus, there exists a delta greater than 0 such that, so what I'm going to do now is I'm going to write this limit that I just wrote down. I'm going to write it in terms of the epsilon delta definition. So such that, and actually this is continuous, so I don't even need the 0 less than here, such that if x minus p is less than delta, then this gross thing, x minus p, f of x minus f of p, 1 over f prime of p is less than epsilon, right? Why do we take the reciprocal here? Right, this is part of this thing where like, you're gonna have no idea really why. Well, okay, here is the reason why. So you'll see in a second that it just magically makes everything work. But if you wanted to, you could look ahead at what it is that we're trying to prove here. Basically, this formula at the top here in the rectangle, I know that this is going to be the derivative. So I know it's going to be 1 over, right? That basically the derivative of the inverse function is going to be 1 over f prime of p. So I need the reciprocal of f prime of p to show up somewhere. This is basically why I'm doing that. Does that make sense? Right? Because I'm looking ahead, I know that 1 over f prime is going to show up. And then, like I said, you'll see that just magically everything does exactly what you want it to do. Okay. So this is true, right? And I haven't done anything. All I've done here is written out the epsilon delta definition of my thing, right? Of this weird limit here at the top. Now we also know that f inverse is continuous, and I'm going to use y just to denote the input for f inverse, just so we can keep track of the differences between x, which is in the domain of f, and y, which is in the domain of f inverse, and therefore the codomain of f, right? So since f inverse is continuous at, let's give it a name, q is equal to f of p. Okay, so I just don't want to say f inverse is continuous at f of p. Let's give it a name. Let's call it q. So since f inverse is continuous here, there exists a delta hat greater than 0 such that if y minus q is less than delta hat, then f inverse of y minus f inverse of q is less than delta. Okay, so you'll notice here I'm not using epsilon. I'm basically using the delta that I got from the above limit as my epsilon in the epsilon delta definition here of continuity of f inverse, right? So I'm using delta and delta hat. It's a delta delta hat proof. It's not an epsilon delta proof, right? My epsilon here is the delta that I got from the previous step, and you'll see why in a second. Okay, so here's the cool thing. Basically, if I unravel this, that is exactly going to be x minus p is less than delta. Do you see that? Do you see that that's true? Right? So this thing here, if I unravel that, this is going to be, let's let x, let's say that y is equal to f of x, right? Again, my function is bijective here, so I'm allowed to do that, right? I know that if you give me a y in the codomain, there's an x which corresponds to it. So I'm just going to let x be the name of that variable. This is going to become x minus p is less than delta. Yes, yeah, f inverse composed f is the identity precisely because that is what the definition of f inverse is. Mm-hmm. Okay, so this is an important one. Is everyone okay with what just happened here, right? So because q is f inverse, because q is f of p, that means f inverse of q is p, right? Right, and same thing, if y is equal to f of x, that means f inverse of y is equal to x, right? So now I have that x minus p is less than delta. Great. So that means So now I'm going to take this thing up here, okay, because we're in this situation now, right? X minus P is less than delta. So that tells me then that X minus P divided by F of X minus F of P minus 1 over F prime of P is less than epsilon. Okay, so I took my y and q, converted them into x and p so that I could use this equation. But now that I have this equation, I want to convert it back into y's and q's, okay? So I'm going to rewrite this as y's and q's. So this is going to give me f of x. Is this what I... x is equal to yeah. X is f inverse of y, right? Yeah, we'd use that even up here, right? X is equal to f inverse of y minus f inverse of q. F of x is equal to y, and then f of p is equal to q. Like so. Okay, and Yuanjie, do you now see the magic of taking the reciprocal, right? So note that when I wrote this thing, even though I wrote this thing upside down, here's a cool thing. I wrote this thing upside down. When I rewrote it in terms of y's and q's, right? I basically took that information in the domain and now have converted it back into information in the codomain. It magically became exactly the difference quotient for f inverse, right? So I think that's pretty cool. And this is exactly the statement. Oops, I'm not using yellow. So what have we proven by this statement? Like look at, actually, no, let's use the yellow again. Look at what I've proven. Okay, if you ignore all the middle stuff, I've proven if y minus q is less than delta, then this thing is less than epsilon. So I've proven that the limit as as y approaches q of f inverse of y minus f inverse of q divided by y minus q is equal to 1 over f prime of p. But this thing is actually, right, if you look at this difference quotient, that is exactly the derivative at q. So this is the formula that I was trying to prove. And because there is no 0 less than here, it actually says that not only does this limit exist, but this limit is actually continuous. Right? And that's what I wanted to prove. Yeah. And, you know, here's the crazy thing. Like at the end of the day, we didn't do any complex algebraic manipulations or anything like that. I mean, the trickiness here is having to translate constantly between f and f inverses and x's and y's and p's and q's. It's a real like nightmare of notation because, you know, again, if you think about like the graph of something, I keep jumping between the x-axis and the y-axis and writing things in terms of the x-axis and the y-axis. And I've tried to do so notationally in a way that's obvious. I could have been like super consistent and written everything in terms of y's and q's, say. But if you do that, I think things get a little bit confusing. So I am kind of jumping. I mean, this is probably confusing too. So I am kind of jumping between them. But yeah, I've hoped that I've done so in a way that isn't too hard to see why this is working. Sure, yeah. So, right, the question is, can you explain why f inverse y minus f inverse q is less than delta? Sure. So we know this fact right here. Right? So we know that f inverse is continuous at q. So I'm going to let this be my epsilon, right? This is the epsilon that I'm using. And so I can find a delta hat that makes f inverse y minus f inverse q less than that epsilon, right? Like It might help as well because the inverse notation might be throwing people off a bit. Think about if I said G is continuous at Q, right? Well, that means I can always find a delta hat, which makes G of Y minus G of Q less than epsilon for any epsilon that I choose. The epsilon in this case that I chose, I'd happen to use delta, right? Because we already know a delta exists, right? That is this delta. Can I feed that through? Whoop, like that. So that's the epsilon that I chose, right? I get to, because I know it's continuous, I'm not trying to prove it's continuous, because I know it's continuous, I get to choose which epsilon I want, and I chose that delta. And it's greater than 0, so I'm allowed to do that, yeah. Okay. How we know the x minus p is true then? Sure. So yeah. So this is because we know in this case, let me maybe use red here. We assume that f is differentiable, right? Like one of our conditions here is that f is a C1 function. So that means that it is in particular differentiable at our point P, right? And because it's differentiable, I can be guaranteed this limit exists. And all I then did is write down what that limit is in the epsilon delta definition, right? And again, in fact, I know more than it just being existing. It's actually continuous. So that's why I don't have this 0 less than here, right? Because I was actually told that the function is continuously differentiable there. So does that make sense? That's good. Maybe not. Okay, sweet. Yeah, and if something doesn't make sense, even after I've explained it the first time, it's totally okay to say, no, I still don't understand, right? Like, I just want to do this because I know, for example, back in the day, I can't get the body language clues from you anymore, right? From all of you, right? This isn't directed at any one person. I remember back in the day, people would come to my office and they'd be like, I don't understand this. So I would explain it. I said, does that make sense? And then they would look like super uncertain. They'd be like, yeah, I guess. And I could read, it's easy to read from a student when they're just saying that, right? Because they don't want to keep saying like, no, I don't understand what's going on. And I'd have to say, do you actually understand it? Or are you just saying that? And they would say, I'm just saying it. And then I would be like, okay, well, let's do it again. And in a slightly different way this time. I'm fine doing that, everyone. Like, I have no problem. Like, if you don't understand something, just say, even after I've explained it a second time, just be like, I still didn't understand. And don't worry about holding up class, because if I do think it's holding up class for too long, because we've been working on it too long, I will just say, hey, listen, let's talk about this at the end of class or something, right? Because there's other stuff that I want to do. So I never want you to hesitate to just be like, I still don't understand, right? Exactly. Yeah. Please help me, right? So even if you ask me a question and I explain it, just, don't say that you understand something until you understand it, because I will assume that you understand, right? And if you don't understand, that's my job. My job is literally to help you understand, right? So, but you have to tell me that you don't understand. And again, as a teacher, I can do that. If we're in person, I can read your body language and your visual cues, but obviously I can't do that, right? As a general rule. I think, I actually can't see Stephen right now, but maybe you have your video on. Some of you do, I know, but because I'm sharing my screen, I only see like 4 people's screens and they're all currently off. So, but yeah, you have to tell me, right? Okay, so everyone's good. Are there any more questions about this? Or maybe let me zoom out, you can see the whole thing. And you can imagine this proof actually would have been a lot longer if we had to prove some of that stuff too. So I really banked on term test 2 question 3, right? So that was nice. So I didn't have to actually prove that ahead of time. Otherwise this proof would have been longer, or I'd have just had to prove a lemma beforehand. And then, yeah, you work it out. Oh, you know what? Let me explain where this formula comes from. So you can't use this. This isn't a proof. But what we can say is note, if you know that f and f inverse are differentiable, right? And remember, a big part of the inverse function theorem is precisely that it tells you that your function is differentiable, right? For the last yellow box is that, yes, yeah. So I guess, yeah, I didn't quite write it the same as I wrote it up, or actually I kind of did, right? Here, where I wrote y is equal to f of x, but if you had done q equals f of p and put that in here everywhere, you would have gotten like that, right? And that is what we showed. So yeah, it's true. I was a little bit inconsistent, I guess, with the notation, but yeah, if we use q and p there, then we do get the right thing. And I mean, most of the time, the way we're going to use it as well, we won't be talking about, you know, whether you're C1 at a single point, you hopefully will be C1 on a whole interval, and then you'll be using this theorem implicitly at every point in the interval, right? Okay, yeah, so if you, does that make sense? Hopefully, like, let me know if it doesn't, but I think that was just a confirmation, right? Like, yeah. So if you know that f and f inverse are differentiable ahead of time, then what you can do is you can differentiate f of f inverse of x, right? And this thing, by definition of the inverse, right, this is just equal to x. So what I've done is I've taken this equation, f of f inverse of x equals x, and I'm going to differentiate both sides. Now, when I differentiate the right-hand side, that's very easy. So let's focus on the left-hand side here. So here I'm going to use the chain rule, right? So derivative of the outside evaluated at the inside times the derivative of the inside. And let me, you know, maybe put this in square brackets just to really be clear here. That's equal to 1. This is the thing I'm after right here, right? I want to figure out what is the derivative of the inverse function. So all I'm going to do is solve for it. Is 1 over f prime f inverse x. There you go. There's the formula, right? And again, you can make it look exactly like what we have above by writing y is equal to f of x, or f inverse of y is equal to x. And then if you do it that way, this equation becomes, no, I guess here what I've done, I've been sloppy. Let me change this to y, because that's what we were using above. And I don't want to confuse you in notation by suddenly using, like, interchanging the roles of x's and y's. Okay, so I've just changed all the x's to y's. And so now, again, now here I'm going to say y is equal to f of x. And now if I don't want any f inverses to show up, I get that equation, right? So what you can see from here is that this formula, the formula basically in the yellow box at the top of the screen, is just a direct byproduct of the chain rule, right? Like, I basically applied the chain rule to the defining equation of the inverse, right? That f composed f inverse is the identity function. I differentiate that, apply the chain rule, and then solve for the thing that I'm interested in, and I'm done, right? Like, that's all I needed to do. But pivoted, like, importantly, in order to be able to do this, I needed this part, right? Because you might say, well, okay, well, why didn't we just do this at the beginning? Why did we go through all of this terrible epsilon delta-ness? Well, I needed to know that f inverse was differentiable, right? I can only chain rule this if I know that f inverse is differentiable to begin with. And one of the key and important things that the inverse function theorem actually does for me is prove that f inverse is differentiable. And the way it proves it's differentiable is by proving that its derivative is equal to this formula, right? So this is how, you know, if you were, you know, let's say you lived 250 years ago or whatever, and you were trying to figure out, oh, what should the derivative of the inverse be? You would have done something along these lines first and said, oh, okay, if the function is differentiable, this is what its derivative should be. Let's try and prove that it's differentiable now, and we'll use our knowledge about what the derivative should be in order to formulate the proof. Because you can imagine there's no way you would know to do all this stuff, right? This is crazy. Like there's a huge kind of jump that you would need to be able to do here. But the critical jump is knowing what the derivative of the inverse function should be, right? But the reality is you cheat. You assume the result that you want to prove, figure out what the derivative would need to look like, and then use that in order to figure out how your proof should proceed, right? And that's totally okay because you're not presenting that cheating as a formal proof. You're just saying, let's assume that I managed to show this. What form would it have to take, right? And then just prove that, yeah, that is true. So that's okay, right? And that's actually a very good like problem solving strategy there. Okay, so we're going to use this a couple times throughout the year. One thing you may have, yeah, exactly, right? So, and this is how you develop your intuition, right? So this is you developing your intuition as a cheating sort of thing, and then you prove your intuition afterwards, exactly. So you all may have noticed that I haven't been talking about, like not once have I brought up exponential functions or logarithms. I am actually specifically delaying those. I am going to introduce those functions to you rigorously. Doing those functions rigorously at this point is a little bit of a nightmare. So we are going to end up using the inverse function a lot later when we start talking about those functions. What we can talk about now, though, is trigonometric functions, right? Sines, cosines, things along these lines. And what the inverse function theorem really wins me here is the ability to now define and differentiate the inverse trigonometric functions, right? So for example, you have sine, and then you have arc sine. I think some of you have heard about arc sine, arc cosine, arc cosecant, et cetera, et cetera, et cetera. The inverse function theorem will very quickly let me prove that these things are differentiable. All right, so let's see an example. So, and maybe it should be a theorem, but whatever. We're going to treat it as an example. Okay, so what I'm going to do is start by defining. So if I even want a chance of having my inverse exist, I need to make sure that my function is bijective to begin with, right? So basically here, what I want to do is I want to apply the inverse function theorem to every point in the domain of my function. So what I'm going to do is I'm going to say define f as, what do I want here? Negative pi by 2 to negative 1, 1. X maps to sine x, we get that f prime of x is equal to cos x, which is greater than 0 on negative pi by 2, right? So f is, in fact, bijective. What do I want to say? F is, in fact, strictly increasing. It's actually strictly increasing on the closed interval as well. On negative pi by 2. And if you're wondering about how you prove the endpoints, you literally just plug the endpoints in, right? F of negative pi by 2 is negative 1. F of pi by 2 is positive 1. And so you're done, right? So f is strictly increasing on here. And f of negative pi by 2 is negative 1. F of pi by 2 is positive 1. So f is actually bijective. Okay, let me draw a picture just in case you're not certain what I'm doing here. So as a picture, all I'm doing is saying, all right, sine is super non-invertible, right? Sine is really not invertible because it definitely breaks the horizontal line test, right? It is infinite. It is an infinite to one function. It's not only not 1 to 1, it's in fact infinite to 1, right? Because it has this periodicity. So what you're going to do is you're going to restrict. If you want sine to be invertible, you have to restrict it to an interval. And yes, there are lots of smaller intervals that I could choose, or my function would still be injective, but we want to capture as much information about sine as we possibly can. So what I'm going to do is choose a half period. That way I actually get all the values from -1 to 1, right? We know that the image of sine is all the numbers between -1 and 1. So I'm trying to find the biggest interval on which I can actually be injective. You don't need to obviously choose -π/2 to π/2. You could do something crazy. You could do π/2 to 3π/2. Right? You could choose the next half period if you wanted to, but what our goal here is to do is to find the biggest interval on which this function can be injective, and this is a very natural one, right? So our interval is always going to have length pi. That's the best that we can do, and I like to center it around 0 just for symmetry purposes, right? So that's all I'm saying here, and look, by how this is worked out, my derivative is always strictly increasing, right? So my derivative is not 0 on the open interval -π/2 to π/2. Therefore, by the inverse function theorem, I locally can guarantee that an inverse exists around every point. And then basically all I do is glue them together in every neighborhood to say that this function is actually invertible everywhere, right? So by the inverse function theorem, I'm being a little bit sloppy here, but again, you can think about it if you want. By the inverse function theorem, F inverse mapping -1, 1 into -π/2, π/2 exists. I mean, we actually already knew it existed because we don't actually need the inverse function theorem to say that the inverse exists because we know the function is bijective. What we will use here is that this is automatically differentiable on -1 to 1 and is C1 on -1, 1. Okay. And I only get the open interval there because you can't even talk about, F prime being defined at the endpoints. You need an open interval around your thing in order to take limits and therefore to, take derivatives, for example. So that's just the only reason why it's an open interval. And the name that we usually give this inverse map is called Arcsine. So here, F inverse of X is Arcsine X. Okay, does that make sense? I think some of you have probably seen this written as that, right? Where you put the little -1 in the sign. I don't like that notation. I think that this notation can be confusing and lead to issues, especially since this does not really obey the exponential rules that you want. So in this class, I will always refer to these inverse trigonometric functions as arc whatever, right? So arc sine is the inverse of sine, arc cosine is the inverse of cosine, and so on. Yeah, well, which one is used in physics, the arc or the -1 in the exponent? Yeah, because they're lazy. But it's even easier to type out. Like when you're LaTeXing, it's easier to type out arc sine than sine inverse, right? Because sine inverse, you have to put everything in brackets. It's very annoying. Okay, so we automatically, notice the power of this theorem already. We define this thing, it's the inverse of sine, boom, automatically know that it's C1, right? We don't have to prove it. We don't have to do a limit definition. We don't have to do anything like that. We already know that it is C1 indifferentiable, right? Sine from arcsine? Probably not. It depends. You'll have to show me about which part in Spivak that is. There's a nice thing here, though, of like really understanding the relationship between sine and arcsine. There is a nice exercise, which I'm not certain I've put on your next assignment, but we'll see. But let's see now how actually we could compute what the derivative is, right? So by the inverse function theorem again, so we're going to have that F inverse prime of X is 1 over, so the derivative of the original function, F prime F inverse of X. So this is going to be 1 over cosine of arcsine of X. Okay? This is gross. You don't leave it as cosine of arcsine of X because this is useless to you, because you don't know how cosine acts on arcsine. So what we're going to do is we're going to do one more step. We're going to say, note the Pythagorean identity, right? We know that sine squared x plus cos squared x equals 1. So that means that cos x is equal to plus or minus the square root of 1 minus sine squared x. Now, for our purposes, it's not both plus or minus. Which one is it? Am I taking the positive square root or the negative one? Why? Yeah, sure. Since cos x is greater than 0 on this interval, right? Right. So we are restricting x. So since x is in negative pi by 2 to pi by 2, cos x is greater than or equal to 0 on this interval, right? So in fact, we're only going to take the positive square root. 1 minus sine squared x. And so now I'm going to plug that back into my formula above. So what did we get? So we got the derivative of arc sine x is 1 over cosine arc sine x, but I'm going to now write this as 1 minus sine squared, again, which is bad notation, but it is what it is. Sine of arc sine, but this is great because I know what sine of arc sine is, right? Sine and arc sine are inverses to each other, so this is just x. So I get that, right? And now I'm done. And this is crazy, right? I don't know. I'm certain that some of you have seen this fact before, the fact that the derivative of arc sine is 1 over root 1 minus x squared. But this is absolutely insane because trigonometric functions have, hitherto been very classist in the sense that the derivative of a trig function was always another trig function, right? Doesn't matter how ugly it was. Derivative of sine was cos. Derivative of cos was negative sine. Tan was secant squared. Secant was secant tan. Cosecant was negative cosecant cotan. Whatever. The derivative of a trig function was always another trig function. Now, the derivative of an inverse trig function has no trig in it whatsoever, right? I mean, there's secretly a little bit of trigonometry hidden inside the expression 1 over the square root of 1 minus x squared, but we don't overtly see anything that resembles a trigonometric function here. So it's sort of left its class, right? It's like the Romeo and Juliet story, instead of the Montagues and the Capulets hate each other and suddenly, they've crossed classes and the derivative of this trig function is now this not trig function, right? Derive this first and work backwards? Yeah, sure, possibly. So, I mean, and we're going to do exactly the same thing when we define the log and exponential, right? So most people define the exponential first and then define log to be its inverse. And we are also going to do the opposite. Like we're actually going to define log verse and then define the exponential to be its inverse. But no, for our purposes, I am actually going to assume that for this class, you did know trig, right? So that I don't have to define that from transcendentals. Right? Didn't like the trig. Yeah, in the trig part anyway. Why did, what do you mean, Stephen? So this is just me rewriting this, but kind of now writing it in a way that made it more clear of what we were computing, just that this is actually the derivative of arc sine, right? Because f inverse is arc sine. But if I just leave it as f inverse, sometimes you forget what it is you're actually computing. This isn't just some sort of generic function. This is, So this is like an interesting thing that we're actually doing. And so we've computed now the derivative of arc sine and we get this. Now, again, so the place where the trigonometry is coming in here, where it's hidden, is we know that trigonometry is related to triangles, right? And circles, but triangles and circles are related. So trigonometry is very much related to the study of triangles, and you can see a triangle here, right? Do you see the triangle? What do I want here? So we have y is equal to sine x, right? So what do I want? So 1 minus, so this is going to be 1, and then I think I want this to be x, right? And then in which case this is 1 minus x squared. Right? So yeah, so there is a triangle here, right? You can see that there's a triangle, but it's kind of hidden in the algebra of a triangle. So instead of sines and cosines overtly coming out, it's hidden in the algebra. And basically it's hidden, the Pythagorean theorem is in there, right? That you can see that there's a Pythagoras going on in there. That's where the trigonometry is hidden. Actually, I might have these two backwards. I might have flipped these two around. And you might be like, oh, why does it matter? And for the most part, it doesn't. But there is an actual proper picture here. Okay, so you can play with that if you want. I like the algebraic approach to this. It's a little bit safer, but it is actually possible to work out what this thing is just using trigonometry. Why did my pen not work? So if you want, and I might have written the wrong picture here. I don't want to spend the time trying to figure it out. Well, let's see. So cosine, so if arc sine x is equal to theta, that means that sine theta is equal to x, right? So if this is theta, sine is what, opposite? Oh yeah, okay. Oh, my picture was right in the first place, right? So opposite over hypotenuse, and then so that gives you this 1 minus x squared. So then cosine of arc sine is cosine of theta, which is root 1 minus x squared over 1. And there you go, you have it. Does that make sense? Stephen, I'm not certain what you mean by arc sine, but because of the arc sine is actually because when you're doing sine of arc sine, things are dying, right? So if you want to figure out what cosine of arc sine x is, you would draw this triangle, and this is how you would actually figure out what it is. Right? Arc sine x is the angle such that if you plugged in sine of theta, you would get x out. So what you do is you draw a triangle whose hypotenuse is 1, whose opposite side to the angle is x. So now you know that sine theta is equal to x. And then you'd say, okay, well, what is cosine theta? Oh, it's root 1 minus x squared, right? And so that's where the triangle is coming in here. Does that make sense? I would not recommend doing the triangle. The problem with the triangle is you don't actually know whether you get the plus or the minus sign, and you have to think about it algebraically. So I would recommend sticking with the algebra here, but there is something nice about being able to make these triangle arguments. I think that is nice and that is cool. Okay, so I'm not going to do them for you. They're easy. No, arc sine x is equal to theta, right? Like up here. And I'm using theta here just to remind us which part is the angle and which part is the length, right? So if you've got cosine of arc sine x, then arc sine x is equal to the angle, right? That's how arc sine works. It gives you the angle. And then you're trying to figure out what cosine of that angle is. Yeah. So I'm going to leave arc cosine to you. Your next assignment is going to have you do arc secant, and it's going to have you do it in 2 different ways. So unfortunately, you run into this trickiness where you can see arc sine actually depends. In order to be able to define arc sine, I had to explicitly restrict sine. And you could say, well, what would have happened if I had used a different interval? Would I have gotten the same derivative? Maybe, maybe not. So in your next question, you're going to do arc secant, and this is actually going to make a difference. In arc secant, you have 2 natural but different choices of what the interval you should use is. And depending on which one you use, you will get a different answer. So if you check some books, they will tell you the derivative of arc secant is 1 function. And if you check other books, they'll tell you the definition of arc secant is a different function. And those functions are different, right? They're not just the same function written in a different way. They're fundamentally different. So you might then go on and wonder, well, how could this be true? How could people be saying that the definition of arc secant is 2 different things? It's because they're changing the definition of arc secant. And the definition of arc secant, therefore, is depending on what we use as our interval. right? Like where we make our cutoffs. So in your next assignment, I've tried to scaffold it out. I've tried to make it very clear about what the intervals are and how to go about it. There is a little bit of trickiness in doing arc secant. So just start that one maybe a little bit earlier rather than sooner. For example, one of them has an absolute value in it. But yeah, so that'll be, I think, kind of an interesting thing. But for sure, make sure you do arc cosine on your own and arc tan. They're not hard. There are natural intervals for them. And just, again, fly through this computation. It shouldn't take you more than a couple minutes for each one, but make sure you get it and are comfortable with how you would do that. Okay, so that's going to finish us off for this week, everyone. Thank you very much. Yeah, I don't think that there's anything pressing. I mean, obviously, I think there's an assignment, right? But whatever. If there are any last minute questions, I hang around for a little bit. Otherwise, you are free to take off. Thank you, everyone. Thank you. All right, nice. All right, have a good weekend, everyone. And I will see you on Tuesday or Monday if you're coming to office hours. Sure, a question for assignment question 2. Sure, let me just pull it up. Don't mind hanging around for a little bit. Yeah, let me pull it up so I remember what it actually is asking you. So for assignment 5, yes, direct messenger.
Is it all right if I talk?
Sure.
Yeah, okay, nice. Hello. So when we say the derivative is superior to 0, does that mean that, like, for an A, just a little bit smaller than C, and for an A just a little bit bigger than C, the tangent AC, sorry, is going to have a coefficient superior to 0? Like, even if, let me rephrase it, even if like C plus H is bigger or smaller than C, the tangent is going to be the same one, and is going to be its coefficient is going to be superior to 0. Did I explain it right, or am I just confused?
Did you say its coefficient is going to be what? It's square root of 0?
No, superior to 0.
Superior to 0. Okay, well, so notice in that question, first of all, it doesn't actually tell you that f is differentiable at C plus H or C minus H.
Yeah.
Right? So you actually don't know even whether the function is differentiable at those points.
Yeah.
So it's impossible to talk about their tangent.
Okay.
Now, the classical counterexample for this, it is actually differentiable there. But yeah, you don't know the... So you can see in the note, right, that it says that this is not the same thing as increasing. And the reason for that is that the classic counterexample to show that this is not the same thing as increasing, the derivative there actually can be negative at C plus H.
Okay. Okay,
right?
I see.
Yeah. So you only, the critical thing about this is that you only know that f prime of C is greater than 0. You don't know it about any points nearby. You only know it at that single point.
Does that mean that we need to use the epsilon delta?
That would certainly be sort of like a good way of kind of going about that. Yeah, because you only know about the derivative at a single point. You can't sort of make any bigger statements about it. The epsilon delta would not be a bad way to go about it.
Okay. Thank you.
No problem.
Oh.
And yeah.
Oh, sorry. And like, something that is a bit weird in the question is that, like, we are defining an interval x minus p, x plus p, and then after that we use h. Like, we use the...
Right, because h is inside of that interval defined by the p's, right?
Okay.
So what we're just saying is that you've got this like x minus p, x plus p, but then h can be somewhere in between 0 and P, right? So you're just making sure you're in that interval when you write down C minus H, C plus H.
All right. Okay, I got it. Thank you very much.
No problem. Okay, everyone's good? Yeah, okay, I assume Nicole's left. Adam, you don't need anything from me? You
No,
good?
thank you very much. Have a
Okay.
nice day.
You too, ciao.